So section 3.3, I kind of want to make sure we understand. Remember when we did the cosine of 2a, I think we actually used sine of 2a, does not equal, let me make sure I put a slash through that, 2 times the cosine of a. And all we did is we substituted values in, and we said, well, what happens if a happened to be any answer? Even go pi over 2, I could go there. So if I said the cosine of let's say let a happen to be the pi over 2, 2 times the pi over 2, and then does not equal 2 times the cosine of pi over 2. The cosine of pi over 2, remember, is that's where it's going to cross 0. So it's going to be 0 times 2, which is going to be then just 0. But then this is going to actually be then pi. The cosine of pi then is going to be 1. And so 1 obviously does not equal 0. So keep in mind that's a counter example for the fact that we cannot, if we have 2 times an angle, just pull that 2 out in front. But when we do the sum of angles, a real common mistake is to say that what happens if I have the sine of a plus b is equal to the cosine of a plus the cosine of b. And you have to, I'm going to just put a big no, so you never look back on your notes and say we can do that, because just finding a counter example will disprove that. And so in this case, if I let the cosine of 30 plus the cosine of 45, I can quickly add those together and find out that these two amounts do not equal. And I could substitute any value in and find out that's not going to be the case. But we do need to have an identity for the cosine of a plus b. And the next page, it talks about how they derive that, because they don't just happen. I mean, just even like on our quadratic formulas, that these identities just don't appear. They have to be proven. And so this is the proof for how they came up with the cosine of a plus b. I'm going to go ahead and we'll talk about this one on Monday just a little bit more, but I want to go ahead and I want you to, at this point, will you help me just accept the fact that if I have the cosine of a plus b, then that's going to equal the cosine of a times the cosine of b minus the sine of a times the sine of b. Now we're going to end up getting the sine of a plus b, and it's going to be, there's some similarities, but what I want you to remember is if you add on the cosine, it's the two cosines together multiplied together times the two sines together multiplied together, and the sign in between must be minus. Okay, so when I'm going to be doing the problems that you're going to be asked to do will be like find the exact value of the cosine of 75 degrees. Now granted, I could put that into my calculator and get a decimal, but what they want to, when you talk about exact, that means that they're referring back to our radius circle. And so remember, we have exact values for 0, 30 degrees, 45 degrees, 60 degrees, 90, and all the way through in those combinations. And so what I want to do is I want to rewrite 75 as the product, or the sum, not the product, sorry, the sum of two different angles. So the cosine of 75 I know is the same as the cosine of 30 degrees plus 45 degrees. And then I can actually find the exact value without having to necessarily go to my calculator and get the decimal equivalent. Okay, so with that, I'm going to apply my identity. So I'm going to go the cosine of A, which is going to be my first one, which is 30 degrees, times the cosine of my A, which is 45 degrees. Then I'm going to subtract, I'm going to take the sine of 30 degrees times the sine of 45 degrees. Now, when we figure this out, then I'm going to go ahead and substitute. I'm going to go back. Remember, my cosine is my x value. So if I want to refer back to my sheet, and I'm going to say 30 degrees, so I'm right over here is my x value of 30 degrees. Remember, is the square root of 3 over 2. And the reason it is because it's that adjacent, it forms that triangle, the 30, 60, 90 triangle, where my long leg is going to be the square root of 3. And so in this case, and my hypotenuse then would be, the ratio is 2. So this is going to be the square root of 3 over 2. If I have the cosine of 45 degrees, remember I created a new triangle that has the same leg. I have a 1 to 1 to the square root of 2 ratio. And so my sine, my value of the sine of 45, of cosine and sine of 45 degrees is going to be the square root of 2 over 2. Now, keep in mind, right now, all I'm dealing with, both of these are going to be in my first quadrant. You can also do summations when you're into the other quadrants. You'll just have to make sure you adjust the negative and positive signs. But then I'm going to subtract the sine of 30 degrees, again, is my y value for the sine, so it's going to be then this one right here is 1/2, times my sine of 45 degrees, which is the square root of 2 over 2. Now I'm going to simplify. Okay, so I'm going to multiply together. I can multiply radicals underneath each other. So square root of 3 times the square root of 2 is the square root of 6 because they're both under the radical. 2 times 2 is then going to be 4. Minus then on this I'll have 1 times the square root of 2 and then over 4. And since I have the same denominator, I can put them all under 4. So I have the square root of 6 minus the square root of 2 all over 4. Remember, never, ever, ever go and say, well, this is just going to be the square root of 6 minus 2, which is the square root of 4 over 4, because that would not be true. Okay, when it's different underneath the radicals, you cannot subtract them. And you will only look at really the coefficient in front if they happen to be. For instance, like if I have the square root of 5 plus the square root of 5, then that's 2 square root of 5. In other words, I have 1 here plus 1 here, similar to our like terms. Forget to learn in algebra. All right, the cosine difference. What happens if I subtract the cosine? And again, this is going to show you the whole steps on proving that identity. And then your identity is going to be then listed on the next page. Notice that on cosine, if it's a minus, then it's also going to be the plus. And this time we're going to do the cosine of pi over 12. Now, a couple of ways you could do this. Remember, pi over 12 is going to be half of the pi over 6, which is going to be half of 30, which is 15. So you can use that, or you can and convert into 15 degrees, and then figure out from there that you're going to take the cosine of then 45 degrees minus 30 degrees. Or you could keep it as pi over 12, because if I think about it, I'm still going to have the cosine of square root of 45 degrees, remember, is pi over 4. The cosine, the 30 degrees, the radians, is going to be pi over 6. And then in this case, then I would combine my like terms, and then I would go ahead and subtract. So let's go ahead and just do that first one. I have, remember, pi over 12 is going to equal 15 degrees. And so does 45 minus 30. So let's keep it as degrees, but again, you can keep it as radians as well. So I'm going to go the cosine of 45 degrees minus 30 degrees. Remember, it's going to be then the cosine of 45 times the cosine of 30. But this time I'm going to add then the sine of 45 degrees times the sine of 30 degrees. So from our problem we worked, we know the cosine of 45 is the same for the sine and the cosine. So it's the square root of 2 over 2. So I'm going to replace this with the square root of 2 over 2. The cosine of 30, remember I'm going to go 30 degrees, and the cosine is the x value, so it's the square root of 3 over 2. So I'm going to go times the square root of 3 over 2. And this one is going to be then this one. Plus then the sine of 45 is the square root of 2 over 2, and the sine of 30 then is going to be 1/2. And so in this case, then I'm going to go the square root of 2 times square root of 2 times the square root of 3 is the square root of 6 over 4, plus the square root of 2 over 4 is equal to then the square root of 6 plus the square root of 2 all over 4. Notice super similar to the one we had before at 75, but if you also remember, we had the difference between the two rather than the sum of the two. Now notice on this one, okay, if they said use an appropriate identity, okay, to simplify each expression. Well, so if you have the plus sign, then you're looking at this is going to equal the cosine of A minus B. Okay, so in this case, if I have it listed here, I'm actually have it in this form because it's plus. That means I'm looking for the identity of the cosine of A minus B, where A is going to be 49 degrees and B is going to be 4 degrees. So in this case, I'm going to go ahead and go the cosine of 49 degrees minus 4 degrees, and that would be the cosine of 45 degrees, which again, the cosine of 45 degrees is going to be the square root of 2, square root of 2 over 2. This next one we're going to prove, so it looks like a little bit like what we did on the last chapter we had on 3.2. So when I have an identity, when you're simplifying and you're proving a complex identity like this, what you want to do is we want to go ahead and use our plus or sum and difference identities. So we start off with the cosine of x minus y. So I'm going to replace that with the cosine of x, cosine of y. But remember, if it's minus, I'm going to go plus the sine of x, sine of y. And again, if you the tool that I give here, again, is going to be this one right here, where I'm going to use these two identities. We're going to talk about the sine of a plus b and then also the tangent of a plus b in 3.4. So I'm going to start by replacing my identity. I have it all over, remember, the cosine of x, the sine of y. Okay, then I'm going to go ahead, remember they said you can work with both of the two identities together. I'm going to go ahead and do this because I have the tangent and the cotangent. So I'm going to change this to the sine of x over the cosine of x plus the cosine of x, or y, excuse me, over the sine of y. And the reason I did that is that I'm looking at this, the bottom, I had a feeling I was going to get something that looks a little bit like this. So when I do this, I'm going to say that I'm going to combine these two fractions, and I'm going to say this is going to be the cosine of x, sine of y. So in this case, if I look at my first term, that means I have to multiply the sine of x times the sine of y over the sine of y, so that way I can combine my two fractions. So I'm going to have the sine of x, sine of y, plus, now if I have then the cosine of y, and I have over the sine of y, and I want to combine them, I'm missing my cosine of x. So I'm going to multiply times the cosine of x over the cosine of x. And that means I'm going to have plus the cosine of, I'm going to go ahead and keep it as x, times the cosine of y, just because I'm kind of looking at this one and it's going to be very similar. Now, if you notice, then I have the cosine of x, cosine of y, plus the sine of x, sine of y, all over the cosine of y, sine of y. And if I multiply both sides of my equation times the cosine of x, sine of y, so it means I'm going to come over here and multiply the cosine of x, sine of y, then both of those are going to cancel out from my denominators. And I'm left with cosine of x, cosine of y, plus the sine of x, sine of y, is equal to the sine of x, sine of y, plus the cosine of x, cosine of y. And notice those are exactly the same thing, except one of them's turned and written first. This is cosine, by the way. So anyway, that's how you can prove that as an identity. So these two actually would be the same. Now our co-function identities. Co means I think about in terms of my, when I have my right triangle, okay, and I knew that this would be like 30 degrees, then this one has to be 60 degrees, and I bet you've actually noticed that the sine of 30 degrees is the same thing as the cosine of 60, and vice versa. And so what happens is on the co-identities, this is also a way that we can subtract them using the fact that you have the pi over 2. And we know the cosine of pi over 2 and the sine of pi over 2, and that's why this is the proof from this identity. We've already proved the cosine of a minus b. And so if I go the cosine then of pi over 2 times the cosine of b plus the sine of pi over 2 times the sine of b, and I know the cosine of pi over 2 is 0 and the sine of pi over 2 is 1, this term will cancel out completely and I'm left with just the sine of b. So that means the cosine of 90 minus the angle, or the cofunction, is always going to be the sine, or the cosine would change the sign. And it works vice versa on any of our identities. So when I look at, if I go the tangent of 90 minus u is going to equal the cotangent of u. If I say the secant of 90 minus u is going to equal the cosecant. And it works the same way and the other way around. Okay, so use the cofunction identity to find the exact value of the sine of pi over 12. Now remember on this one, I'm going to go the sine of 5 pi over 12. Remember, it's going to be the same as my cofunction, so it's going to be the same as the cosine of, and then I'm going to go 90 minus, so it's going to be pi over 2 minus 5 pi over 12. Now, on this one, I think I'll simply go ahead and take, I know that this is going to be pi as a 12. This is the same as cosine of pi over 2 in terms of twelfths, would mean that I'd have to go 6 pi over 12. Remember, 6 over 12 would be pi over 2 minus pi over, or 5 pi over 12. And so in this case, I'm going to go then 6 pi over 12 minus 5 pi over 12, which is be the cosine of pi over 12. Now, at this point, I would use what we talked about before on the last one, because we actually found the cosine of pi over 12 to be the square root of 6 plus 2 over 4. But I'd go ahead and then use I could go ahead and find the exact value of the cosine of pi over 12. Determine whether the cosecant of x minus pi over 2 is equal to the sine of x as an identity. So the first thing we want to do is we want to rewrite this as one of my identities. So remember the cosine of let me just go alpha minus beta, so we just write it down, so and you can put any values in there, would be the same as the cosine of alpha, cosine of beta. Then remember, if it's minus, it's going to change to plus, the sine of alpha, sine of beta. And now what we're going to end up doing is we're going to change this to the cosine now of x minus pi over 2. So I'm going to leave it as the cosine of a is just going to be then the cosine of x. But now I'm going to have times then the cosine of pi over 2. Then I'm going to go plus the sine of alpha, or x, times the sine of pi over 2. From what we learned last time, if I had the cosine of pi over 2, which is 90 degrees, again, if you struggle with that, grab your thing. Remember, 90 degrees or pi over 2 is the same as coming up here at the point 1, 0. So this is my x and my y. So my cosine is going to be 0. So this is just going to be then the cosine of x times 0 plus the sine of x times 1. And the cosine of x times 0 is just going to be 0, so I'm left then with the sine of x times 1, which is just the sine of x. And that's my proof of my identity.